if you're using a tree-based model like the boosting models, they can actually figure out which features are most important.
And so, do these boosting-based models, they also work on numerical values, or they only work on categorical, like 1 or 0?
No, they work on.
They absolutely work on numerical values, and this is the variable importance, and we're going to see that now much more significantly in this next presentation.
Okay.
Okay. So let me just. Okay. So actually, what I did here was I took the IBM data set that we talked about, that I talked about a while ago, and remember I built models using Ridge and Lasso. So I mean, all these first slides are just going over the fact that I took this IBM data. I took 6 days, and I created. Actually, I think I used it was the model up. The next on day 6 was it up? You know, slightly less than 1%. 0.9% over day 5, just to get a reasonably balanced. I think with this way, it turned out to be about 23% of the time this was true. So, you know, I don't want to go over this. It's just what I did before. I had the 6 days. I created the ratios of the different days. I created a bunch of moving averages, I looked at some medians, I looked at momentum, and I looked at RSI. And then I added logs of the variables except for momentum, because momentum takes negative values. And then I had this huge data set that I had, well, huge, I had 55 variables. And the first thing, and this is just one thing you could do, and this is what I did. So I loaded Caret. I'm going to use XJBoost, but before I did that, I wanted to look and see whether there's some highly correlated variables I could get rid of. And so another function that Caret has is something called find correlation, and it uses a default of 0.9, but you can change it to whatever you want. And what it does is it finds the indices of the most correlated variables. And what it does is let's say it says 2 variables have a correlation of bigger than 0.9. So you want to remove one of them. Which one does it remove? It goes and looks and sees which one has the higher mean correlation, average correlation to all the other variables, and removes the one. So it removes the one for which you're losing the least information possible. And it goes through all the variables iteratively, and it does this, right? So in the end, it gives you back an index of the variables that it sees are correlated and says if you want to remove them, these are the ones you should remove. So I did that. So I said remove variables is find correlation, and you just give it the correlation matrix. So I did. Remember, IBM.x variables are all the variables, and I sorted them to put them in order, and it said you should remove, and I thought this was most interesting, because it said you should remove all the actual data. Day 1, day 2, day 3, day 4, and day 5. And then you remove about half of the ratios, most of the moving averages, and then some of the others. Mean, it said remove, you know, you could see it's saying median.5, median.11, and most of the logarithms went too. So you might ask, well, what's left? And so it said, actually, if you're going to remove variables that are greater than 90% correlated, these will do, these 14. These ratios, so you had 6 ratios. It said keep a couple of momentum, a couple of RSIs, and just a couple of the logarithms, okay? So let's do it. So I just sort of, but I said, you know what? Call me a sentimental old fool. I want to keep one day's variable. So I just took day 5, the last day, and I took the variables that selected, and I did that. And this is just a very long But if you were interested in seeing any correlations, you can see now that it's not too bad. The variables, there's lots of, there's some reasonably correlated, but this seems to be a reasonably independent set of variables. So this was something, and to do this in Caret was very, very simple. All you had to do was run this one function, find correlation, and you run it on the correlation matrix. So this is the kind of reason why Caret is useful. All right, so test and train. In deference to standard practice, I mean, I kind of have my own feeling, and I really want people to argue with me and convince me, but I kind of feel like, data, it evolves in time, but there's some sort of universality. So if you take 6-day segments of data, you don't really need to, just only take 6-day segments from before a certain date, and then, for your training, and then test on 6-day segments afterwards. But it's not bad. It's easy enough to do. So I did it. So there was like, I think there was something like 950-ish. Well, I can tell you, 957 days of data. So I used the first 700 for training, and the next, and then I said, well, we don't want any overlap. So I skipped the week ahead, and I started 706 to 957 for your test set. And much like GlimNet, it wants sparse, it likes sparse, it likes these model matrix objects. So I just created those to use it, and it just, XGBoost likes them, and it works very well with them, and it's faster with them, so I did it. So train-X is just sparse model matrix of the data. And with what you're doing is, this is really useful if you have categorical data. This is good because it'll do any one-hot encoding or creation of categorical variables that linear model or some of these other packages demand. So if you do have, categorical variables, you do want to use model.matrix or sparse model.matrix. But I just did it anyway. Okay, and then I just ran one model. So what did I do? So XGBoost is doing this gradient boosting. And I said, use the train-X data, and the label is a categorical problem. I used train.labels. Now, remember the train-X is the matrix model, doesn't have the labels. Labels was 0, 1. 1 if the model on day 6, if you have 5 days of data on day 6, it was up more than 0.9%. And then I just sort of randomly picked values. Max depth, trees of at most 4. Eta equals, that's the learning rate, is 0.01. Verbose equals 0. Don't tell me everything that's going on. If you're doing multi-core, and threads will say how many of the cores you should use. And I said, do 5,000 rounds of training. Do it 5,000 times. And this took almost 30 seconds, incidentally. So you can imagine when you're training a large number of hyperparameters, this can take a while. Okay, so, and then I called this model 1, and you can see this is the information. It just, nothing particularly interesting. It just gives you the information. Okay, now we were asking, how do you decide which variables are important? Oh my God, Windows has detected something. Phew. Fortunately, I was able to tell it to go away. So when you do these models, remember when you do a tree, and every time you have a split, what it's doing is it's picking a variable and deciding which variable gives you the maximum decrease in randomness, right? And so when you run these things, random forests or gradient boosting, the models keep track of overall every single split, which variable it used and how much it decreased your randomness. And then it adds them up. So variable importance just tells you when you ran this thing, how, which variables did it and which ones didn't. So this is interesting. I demanded that I leave the underlying, which was at day 5. And gain is the important one. That's sort of measuring how much of the percentage of the randomness came from that. And that was the most important variable in this. And then it says the log of the ratio from day 3 to day 2, and then 5-day momentum. And you can see, but you can see this, Manish, answers your question, and you'll see more because later on, what I'm going to do is I'm going to take less variables. And what you would do is you would sort them by variable importance. And you can see down here, you know, these last, there's a bunch of them that are about 5%, but maybe you'd cut it off or somewhere around here, 6% and that. And this is just a graphical representation of the same thing. You can see underlying, when you let it in, was indeed the most important. And I said gain is a measure of relative contribution. And you can see that when you look at the importance of all the gains, they do rate up to 1. So cover and frequency, I get them confused, but I wrote them down. Cover is the relative percentage of observations for which the feature occurred. And frequency is the percentage of the times that feature was used. So cover is on, you know, sort of, you know, where you split it in the tree, and then feature frequency is how many times. But gain is the only one that really is useful. I mean, it's the most important one. I've never had a time where I particularly was interested in frequency or cover. I'll put it that way. So that's just one model, and you want to use it. Well, you use the predict. So the predict function is very simple. I have this model. I give it my new data, and it gives a prediction. So just you can see, it's predicting, in this case, numbers. Now, if you might have noticed, I didn't tell it to run as a probability model. I don't know if it's a bad habit or a clever idea. I don't do that. I do this a lot because in the end, you're going around, as long as it's nothing too stupid. You know, I've never had a situation where I got anything but zeros or ones when I rounded. So it just seems it's a different way of doing it. I mean, you can, and you'll see a little bit later, I can make the gradient boost to say, no, this is a probability model. I want all my values to be between 0 and 1. But in any event, I consider these as if they are probabilities. And I just, oops, sorry. What do? I say, well, I'm going to give it the random, the canonical example. I'm going to, predict, 1 if it's bigger than 0.5 and 0 otherwise. And then I can measure, when it's, I can measure how accurate it is by saying, well, I have this as numeric, and my prediction is bigger than 0.5. That's going to be 1 or 0. I can say, so that's going to be equal to, does it equal the test label or not? And I'm either going to get 0 or 1, and that'll give me an error. And so I got an error rate. Oops, excuse me. On my screen, the sharing thing is sort of right on the bottom, and I can't get it to move. So, wait, maybe I can now. Okay, there. Sorry, now I got it. Okay, great. So the model was about 78% accurate. But don't forget, I just randomly picked this. No particular good chance. Now,
so did we check like the importance of the variable? How much did they stay same in test versus train, or they changed?
No, I mean, you see, you only use the variable importance only occurs when you train the model.
Right.
You see, so now I have a trained model. I have an actual formula, and now I use predict to apply that formula to new data. I'm not creating, so the model's been fixed. I mean, the variable importance only comes from the training set, because you only use the training set to create the model.
Right. What I'm saying is, like, if the variable importance in training set and test set are different, then probably it's kind of a data which is hard to predict.
Okay, let me rephrase my answer. I don't know what you would mean by variable importance on a test set. Variable importance comes by creating a model. You take a data point and you run, excuse me, I'm getting a little sore. And what do? You find the variable that splits all the data the best, right? So let's say you're just doing a world's dumbest model. You're just going to do one split into two, right? So you would have the variable importance would be only one variable and one value, right? So the variable importance of that variable would be 1, and the variable importance of every other variable would be 0, right? Now, what do you do when you do the test data? You just apply this model. You don't find any more splits, right? You already have your split, and you just apply it to the new data set. So you don't create variable importance on test data. You only create variable importance on the test data, because it's on the test data that you play with what variables you're going to use and what values of the variables you're going to use for your splits.
Right. I got that point. Okay, let me just rephrase what I was saying. I'm saying, like, let's say if you use your training data, right, and you run a model, right, and this gives you
Create a model on the training data.
Yeah, you create a data model on your training data. You create variable importance, correct?
Right.
And
you can find variable importance.
Variables are important, and then you predict. But let's say now you are ready to run your model live, right? But before doing that, probably you may want to see, let's check if I use my test data as training data. Let's use my test data and train my model using test data and see what's the variable importance coming out to be. If that variable importance coming out to be very different than what came out with the other split of the data, then probably this data is something which may not be very stable when we run live, because things are changing so fast. There is no stability between different splits of data.
Okay. The one rule about test data is it gets one shot. Now, what you could do, Manish, is you could have divided the data into 3 pieces. You could have created a validation test set. And once you have your model, then you could see on a validation set, when you reran it, did things change? But you never play with the test set. The test set gets one shot at the model and one shot only, and it is your analysis of how well you think it's going to do on more raw data. Right. Now, what you can do is you could, rather than just doing this in one shot, and don't forget, we haven't done Carrot yet. All I've done is I've created one model. What would you do? Well, you could show it the training data as many times as you want. So you may want to show it the training data a bunch of times in different orders.
Yeah, you can do boosting on training, or you can do a boosting on training, and you can see how.
Or you could use cross validation, and we will. You know, and once you have the whole thing done into a package, there's no law that says you can't run that whole thing 500 times and see across 500 times, is there stability in what you get out? Right. And in fact, this is kind of where we're going here. Yeah. But right now, I mean, so you can do it sort of, but you don't do it. The one thing you don't do is you don't do it with the test data. You can take the training data is Play-Doh. You can do with it as many times as you want. I mean, there's absolutely no reason with modern computing that once you create a procedure for finding your ultimate model, that you shouldn't run it 500 times and see that it comes out reasonably correctly, or that there's a reasonable stability in what it chooses. Not only can you, but you absolutely should, and we will. But with the training data only. All right? But right now, we haven't gotten to Carrot yet. We've just created one model. Okay? Aha, your question was really propitious. So you do want to check all these things. You don't want to just produce one model. You want to produce thousands of models, and you want to tune over hyperparameters, and you want to see how things work. and then you want to rerun with things, and we're going to do all this. Okay, so we're going to do this in Caret. So remember, train control tells us how we want to tune, and then optionally you can give it a grid of parameters. But Caret, while it needs a train control, has a default measure of how many values it will use. So if you did want to do it, it's this. So train control, I'm going to give it the method is cross-validation. The number is 3. And I'm just doing this. I'm giving it. I'm doing a small number cross-validation. It's not a good idea, but it makes the thing run quicker, which is why I was doing it. But I mean, I would do, as I said, 10 repeats of 12-fold cross-validation probably in real life. Okay, and here I'm seeing, you see class probs equals true, summary function equals 2-class summary. I'm telling it now that it is a probability model. And now I'm giving it a lot of options. Well, not as many as I would. I mean, in particular, I would instead of, I would run way more rounds. I probably leave the maximum depth that where it is. Gamma, all these things. These can be greatly expanded. Just a question of how much computing power and how much time you have. But here you have. This is what I'm going to do. The other thing, I might do verbose iteration equals false. I did it all over again. Okay, so now, unlike XGB, Caret likes matrices, and so this just works. This is you read what the literature from XGB and from Caret, and this definitely will work. So you might as well do it. You make it a matrix. You have my training data. I just remove the labels. I say my Y values make names. That's a formal R term for creating factors with good names. I've already given it its train control, tune control, and unfortunately, it now goes through everything I've done. And now I have a Caret object, which is XGB.train, which has all these different models. Now it has a bunch of models. This did not run in 20 seconds. All right. So, and remember, I did do some cross-validation, 3-fold only, but it's better than nothing. And I do have it. And so before I said the resample function, but it's just a value of this model. So I cross-validation sample is the model resample, but there's also another piece of the model, which is resample CM. This contains the information you need for the confusion matrix. Now I could compute my number of folds, but I know it's 3, and the number of models is the number of rows in this divided by the number of folds. And the cell 1 through cell 4, those are the 4 cells of the confusion matrix. So I just need that. Okay, so, and here it is. I tell you true positive. So surprise, surprise, true positive and true 1 are cell 1 and cell 4. The only thing worth knowing is false negative is cell 2 and false positive is cell 3. So it does work like, R, because R, when you give it a bunch of numbers and say make it a matrix with 2 rows and 2 columns, it reads down. So number 1, number 2, number 3, number 4. Okay, and so now I could show you after I've done all this thing, what have I done for each model? It's given me the information of what specific, what were the specific value of the hyperparameters. And here it's computed the various things, ROC, sensitivity, specificity, and I think that's true positive and true negative. And then it's given me the 4 values of the confusion matrix. I'm going to point out to you that this 11, the cell 4, the cell 4 is the times I correctly predicted that it would go up, and we can see that's not very good, and that will continue to be an issue. And all I'm doing over here is, this is a little bit of fancy stuff that basically is, I did 3-fold cross-validation, and I'm interested in getting all this information for each fold and adding them up. And that's what I'm doing, is rather than going, I've just figured out my own way to sort of group by or roll up by the different folds, by the different times I did cross validation, and I roll them up. You can see I just take the averages of all three, and I just create this. And all I'm doing is I had 48 rows corresponding to 16 models, 3 running across validations, and I just now have something with 16 rows. So because I've done this, we can have some fun, which is to say we can ask a better question than just how well did the model did. You know, we don't really care about the sum of the true positives and false negatives. We really only care about the true negatives. The self form. I think I wrote this wrong, but okay, so this is showing you the matrix I've created. I now have all these things are merely the parameters I've chosen, and then I have the 4 values: true, positive. You know, why are they fractions? Because remember, I added up 3 of them and divided by 3, and I've ranked them by, you know, basically by model rank. I think model rank was how well it did on true negatives, which is all I really care about. So maybe I skipped over that. Yeah, model rank is just, it's just the how many of the ones that went up, you know, 0.1, 0.9% did we get right. So you can see I had a bunch of, so this is the first 6 models. And they're all, unfortunately, pretty much the same. They're not doing a very good job on this true negatives, which is what I care about. So I have all these parameters. I have 7 of them. You can see them here: ADA, max step, da-da-da. Now, I want to extract the top feature choices. So what I do is I have, I'm going to find the top, I'm going to take all the top models, I'm going to create a list of them, and I'm going to get the variable importance for each of them. So this is Y3 because there were 3 folds. I'm just going to take the top 3 models. I would probably keep 5 or 6 in the real world, but again, to keep calculation short, I only took 3. So I create a parameter list, which is the parameters for the first 3 models. And then I run a new model with these parameters. And here you can see now I've got switched to binary logistic, which will give me probabilities between 0 and 1. And now I've created new models with just using these top parameters. And more importantly, for each of these top 3 models, I've created a list of the variable importance models, of the variable importance. Now the point is that the variable importance is not just going to give you the variables, but it's going to give you the gain. And then this goes on for quite a while for most of the thing, because I couldn't figure out how to say, don't display this on this. So now you get to see me scroll over a bunch of stuff. Now you're showing very small training errors, but don't forget this is on the, you know, the training data, not the test data. So it almost takes longer for me to scroll through this than it took me to write that little bit of code. But in the end, we'll be there. I couldn't figure out how to suppress the output in there. So I had, you know, these 3 things. Bind.rows says you have this list. And the list really isn't a list of data items like a matrix, so make it into a matrix with all of them. So I variable importance models is that. And why does it not have more of that? And now it's ending there. Oh, 1 second. Okay. Okay, so this is where we were. And so I took all the variable importance and I ordered them by the gain. So from most important to least variable. And I just arbitrarily said, let's keep the top half of them. Okay. So this is getting into what you were asking, Manish. How do you decide which one? So here I did. I ran three. In the end, I ran three models. If I was doing this with more time and better computing power, I probably would have run top 5 or top 10. I would have had way more than 16 models to start with. And now I'm going to look at all the variables that are important. And in fact, it turns out that this came up with 12. And so these are the 12 variables that I'm going to use. Okay. So I now have 12 variables that I decided are actually giving me good information that are contributing to the model. And now I'm going to go back and retrain and pick these top 5 models using just these features. Again, well, two things. First of all, we haven't seen the tested yet. And secondly, you might want to go back and rerun it on everything. I mean, I'm just, for the simplicity of time, I'm taking those 5. I don't know, my stuff did not compile correctly. And it's showing I ended here, but I did not. I have way more, I have more stuff to show you. So you can either view that as a good thing or a bad thing. Oh, here it is. Okay. So keep in mind, and as I said, we haven't used the test set yet. This is, and as I said, more complex data. If you were doing this more fully, if this was somebody was paying you, serious money to do, this might be the spot where you use a validation set to check things. And you really want to check that taking these variables increase the importance. But this first piece of code is just saying, I want to only use those variables I decide were important. And now I'm going to redo everything. I have the parameters for those models. I'm going to redo the models, create new models that are only using those variables I decided were important. And I'm again creating keeping track of those models and the variable importance. Okay, so again, this is just going through and same thing. And then I, again, put them all together. Okay, so now we're finally ready to look at things. I have at least the first draft of final models. I have 3 models. Actually, I have 3, not 5. I don't know why it says 5 there. And I want to see how well it does. So it works perfectly. It correctly classifies everything on the test set. And here you can see this is of the individual models. But now it's time to see how well we do with the test data. Spoiler alert, not as well. Okay, so now I created something to keep the thing. So now I look on the test set, and again, I just use predicts. I have my models. I have my 3 models that I've done, and I have my test data, which I make into a data matrix. And since I have 3, if I want test prediction to be bigger than 1.5, that's better than 55. And it looks pretty good. I get 194 out of the 250 cases. But tell them the bad news, Mortimer. It's absolutely crappy on what I care about, which is the class that went up. It only gets 2 out of the 59 cases right. So it's really bad. It's a pretty good model, but it's a pretty good model because the cap on this model on this would be terrible, because random accuracy is essentially random accuracy. And then I looked at the individual ones to see if maybe one did better, and no, they all just do pretty crappy. And on average, they do pretty crappy because they all do pretty crappy. So what did I do? I said, well, maybe it'll work better if I'm more strict. And the answer is no. If I say I demand that they each have a probability, on average, the probability is 60%, I do very well. I only get one case in which I predict. So you were 40% accurate, but it only picked out 5 instances. I don't know where this is coming from. That's wrong. But I did look. It basically said it predicted 5 cases to be true to be rallies, and it got 2 of them were correct. So it was 40% accurate as opposed to 27% accurate. But when 5 out of all those cases, that's not helpful. Okay, so wow, I'm doing pretty good on time. I'm very pleased with that. So what next? So if I was doing this for all, first of all, I'd rerun it with a much larger set of hyperparameters to search over. I really know I gave myself short shrift in there. I mean, in particular, frequently n rounds equals 5,000 or 10,000 will include your best things. I'd consider forcing prices into the variables I'm going to use. I would create more features, and I would also consider using longer lookbacks. Those are some of the things I would do right off the bat. And my last slide, my last words is, what would you do? And that's all I have to say. But you can see, Manish, that when you really start doing these things, it's not just as simple as you run a model. It's not even as simple as you run 100 models. If you run hundreds of models, and then you start looking through them, and then you say, all right, it looks like these are better, and then you rerun them. And it's an iterative procedure.
Right, so probably, I think when we are running hundreds of models, like the model fitting is happening on each of those 100 models in a different way, right? So each of those 100 models are trained independently. Like it looks at the data, it looks
right. Each model has, you have a different set of hyperparameters that define how the model is created.
But in real life, you will detect these kind of problems because you will fit a model, and then probably if you look at this model by different size buckets or different sectors, that let's see if it's a robustness for how many sectors is it working for, how many, let's say, is it working for both large cap, medium cap, small cap, is it working across like different volatility buckets. You will not go on and fitting different models by different characteristics. And I think probably that's what it is doing, and then it's fitting very well, and out of sample, it's failing.
Well, I mean, the logical, the canonical statement to make about what happened tonight is that the models were overtrained.
Yes, yeah, exactly.
So how do you deal with overtraining? You either train less or you get more data.
Right.
I would think more data is the real answer. And bluntly, I mean, so another thing you can do, and we haven't even discussed this in this class, and it isn't important, and it works, it really works, is, almost all models have problems when there's class imbalance. I took it down to a little bit less than 1% to get the class, up to north of 20%.
Okay.
But you could make a point that, well, there's a lot of noise, What does it mean to be, IBM was up 0.25% today versus down 0.25%? It could mean that, the good buyer of, of IBM had, a bad lunch and decided to take the afternoon off. It's too fine a thing. So you'd probably want to have a more realistic, really care about level. Something that you could realistically say, like, 1.5%, something that was only occurred 10% of the time. And then the real issue is, how do you deal with the fact that 90% of the time your model is going to, your random accuracy is 90%? And there are different ways of dealing with that. We have not discussed oversampling, undersampling, and my usual particular favor is something called smoke. And I won't talk about smoke because we want to go to sleep tonight. Well, I do, you know. So, and I can talk for a long time, but you know, there are ways of dealing with the issue of unbalanced classes. And so I would bet you that if instead of using my, you know, my level of 0.9%, I use the level of 1.5%, something where, you know, you had 5-10% of the time, and then use SMOTE or something. And how you do this is a little bit subtle. I will say one word about that. But if you've done this correctly, you can create good fake data that will really work for the model. And so here's the point. I mean, you can underrepresent or overrepresent, and those are okay. SMOTE is, if you have a really good set of variables, if your variables, what would you mean to me? So a rhetorical question. What would you mean by saying that I'd found a good set of features? What I would mean is that, you know, if you have a feature and it's positive, most of the time near that feature, it stays positive. If you have a point and it's negative, most of the time near that, it stays negative, right? So you've gone into a big enough space so that, you know, you really, you know, in some sense have separation between your two classes. And there are ways you can kind of measure this. And if according to your measures, you do have pretty good data separation, then SMOTE works really well.
Okay. What do you call it? How do you spell it?
SMOTE.
SMOTE.
Synthetic minority over something something. SMOTE.
Right. We do, yeah. I mean, we do it, but not like this systematic way. We call it heat map. We just run it like with shifting the parameters a little bit and just checking what's the impact on the final swap ratio or something.
Right, but you know, and this goes into robustness. You know, if your model says under these conditions we expect the stock to go up,
right,
you expect that if you vary those conditions just slightly, it's still going to say it's going to go up.
Right.
And so SMOTE basically says if you have data like that, we're good, because what it does is it's a very simple idea. It says, all right, I have a data point that's negative. I look at nearby data points. I use K nearest neighbor. And then for each of those data points, I now have a line segment. And I randomly pick another point on the line segment to be a new representative of the class of the center point. So if your K nearest neighbors are working reasonably well, then SMOTE is going to be good. So, and what does K nearest neighbor mean? It means that the points that are close to it work well, you know, are like that. You know, if every time you have a negative example, it's always the case that the 3 nearest neighbors are positive, it's some way of saying you don't have the right variables.
Right.
In fact, somebody, in addition to the SMOTE package, somebody has written, you know, and I was going to write the software, and then I found out it was written. People have written software to sort of say, how well is K nearest neighbor working, you know, for SMOTE? But, you know, it's kind of like a heat map, you know, but it's a mathematical heat map, and it basically says if the heat map's good, then SMOTE will work.
Right. Okay, thank you so much, Adam. So,
All right.
Thank you.
Thanks.
Thank you. Bye.
All right.
Good night.
Yes, nice meeting you.
Same here. Thank you,
Yeah.
Professor. Good night.
See you.
Niels, I think I'll see you pretty soon.
Yeah, I think so.